Hello everyone, this is Ojas Sharma, a bachelor student at Electronics Engineering at EMU. Uh, we are here to show a video on 60 SRAM design and simulations. I would like to thank C2S program at Aligarh Muslim University, which is funded by Ministry of Electronics and Information Technology, Government of India. And I would also like to thank the principal chief investigator for C2S project at AMU, Professor Mohammad Wajid. Today we will be showing you design and simulation of 60 SRAM, which is basically our course project for digital IC course ELE 4620. And moving ahead, I would like to open Cadence. Now these are the commands which we need to run while running Cadence. This is a pop-up window which shows us for about C2, which is for the Cadence tool, which is funded by Chip to Start a Program by Ministry of Electronics and Information Technology, Government of India. We'll be starting Cadence Virtuoso tool over here. Now over here we will be opening a project which is 60 SRAM. Go to our library. We are using GPDK-45nm technology, which is a generalized PDK provided by Cadence. So we'll be first showing you what is a schematic. Now opening Cadence ahead, giving it a full screen. This is our schematic base of a 60 SRAM. 60 makes 6 transistors, that's 1, 2, 3, 4, 5 and 6. Now we also have here the input pins, which is VDD, the VSS pin, the bit line. Bit line is the one which will be needed, which indicates that bit line is on. Bit line bar, the write line, that line will be work as an input. When to write, what is to be written. RB is covered by bit line bar and WL. Okay, so this is actually our schematic with two output pins, which is Q and Q bar. Q is the output we need to check all the time, and Q is bar is the complement for that same. Now we have generated a test bench for the same. I will show you. What is there over here? Okay, so this is our test bench. This is a symbol which we created by Cadence, and we can also customize it accordingly. So we have a symbol for SM cell over here, bit line bar, WL as the left pins, and VDD and ground as the lower pins, with the Q and Q bar as the output. Here I have symbolized my inputs, which is VDD, a DC voltage of 1.8 volts, followed by a word line which happens to be a pulse. I can show you the specs that I'm using right now. So we have from 0 to 1.8. The period of the pulse is 10 nanoseconds. Delay time I'm giving is 5 nanoseconds. You give it or not, it doesn't matter actually. But for more realistic simulations, we have a delay time for the propagation delay that is carried out by two metals and other parasitics. Then we have given a rise time, fall time for more realistic approximations, and then we have the pulse width for how much time it will be on, that is 5 nanoseconds, and the period of 10 nanoseconds as well. So now we check and save it. We would like to do a simulation on this. Currently I have initialized my bit line as 1. Bit line are being governed by capacitances, which are also done in through ICs as well. So once the capacitance is charged, it will become a through path for bit line, as well as once its initial 0, it will be a ground path, as we have studied in digital IC course. They mimic some of the operations, and that's why we are using it. I'll show you. I have initialized condition for bit line currently, that is 1.8 volts, that is logic 1, and bit line bar as 0, as it is a complement of itself, and it's now logic 0. Now to run, we will run simulations. We will be using ADEL session session session. Now when we go for ADEL, we will be using analysis. When choosing analysis, we will be choosing transient analysis. We will use accuracy, develop conservatives, then click on apply. Now to select outputs which to be plotted on design, we will be selecting on designs. Outputs to be plotted is Q bar, and word length, word line actually, sorry, my mistake. Then we will be using the convergence rate given in the simulation. We will be initializing nodes. The nodes which are need to be initialized, Q and Q bar. Now we will be utilizing conditions like, we will be now keeping my Q to 0 and then Q bar to 1.8. Q is 0, Q bar is 1.8. Now click on apply. We'll have to the Q equals 0. We'll be clicking on apply. ADEL will be running this simulation. And this has put on some error. This has put in some errors. I would like to go ahead and verify my schematic as well. Okay, this is my schematic, which is been customized for the layout as well, and everything looks fine to me. I need to figure out what is the error coming up here. After resolving error, we will try to simulate it once again. It still shows up GPDK resistors. Okay, so we will be making it we'll be closing it again. Now we're closing the schematic as well, the test bench as well. Okay, so we have resolved the errors. Now moving ahead, we'll have again launched ADEL. The same things which have been happening, the initialized conditions are same as earlier, 0 for the Q, 1.8 logic high for the Q bar. We'll click on apply and OK. We will try to run this simulation, and we are here running over it. Now the plot has been plotted. So this plot symbolizes basically the write 1 operation, as the Q is now being set to 1 and word line is also transiting to 1, and the Q bar is going to 0, logic 0 actually. So this is how we will have performed write 1 operation over here. Now moving ahead, we will be performing write 0 operation over here. We just need to make some changes. I'll show you them in a moment. Okay, we are back again. So now we will be making few of the changes. We are changing bit line bar to 1.8 and our bit line to 0 volts, or we can say logic high condition over here, as we have specified, choosing the same things and modifying the initial conditions, q being set to 1.8 and q bar being set to 0 right now for the moment. Apply OK. We will be running the simulation again. Now what this operation signifies is, this is read 0 operation. This is how when SRAMs read when a 0 is being occurring over at the input, and simply it resembles it as the output. Now we need to perform read operations as well. Wait a moment. Now when moving ahead with the read operations, we need to just make a slight change, that is make both of the bit line and the bit line bar at the same potential for a moment. That's okay. I will be using ADEL again with the same things. Check and save over here. Close this plot, and we will be using over here now, running the simulations for the time. Now as we can see over here, the queue still uses, as I haven't changed the initial conditions, it will be reading 1. So here the queue reads the 1. The graph here is just because of the deep disturbances, which is a very crucial disadvantage that has been mentioned in the earlier schematics as well for the 60 SRAM. Now this deep disturbance curve can be lowered down by increasing the width of the NMOS, which has been used for the decoupling of the inverters at the lower, increasing the width of the inverters which are decoupled with together, as in the schematic. I'll show you once again. I'm talking about these two inverters. This can be lowered down by using this. I can also show you rate 0 operation. What I just need to do is to change the initial conditions. Go that simulation, convergence in initial conditions, q bar is now 0, and q is 10. Give me a moment, I think there's something occurring. Okay, so there was a disconnectivity. I'm really sorry for that. So what we have done till now is just changing the convergence rate, which I'm talking about. I have changed q to q0 and q bar to 1.8 volts. Set them and run ADDL netlist and run simulator using its spectre over here, and the graph has been plotted. It's over here. Now as you can see, it's at 0 volt. Seeing again the deep disturbance curve, we are still reading 0. Yep, we are still reading 0 over here. Okay, so these simulations are being correct right now. So I don't want to save this right now. I have already one saved. So moving ahead, we will be performing the layout, for which